Have you ever been stuck in the chemistry lab, during a practicals period?
Oh, I think we've all been there.
And you're just mixing things. You take acetic acid, which basically smells like that strong vinegar you have at
That
home.
really sharp, stinging smell.
Yes, and you mix it with some ethanol. You add a tiny, tiny drop of sulfuric acid, heat it up a bit, and then suddenly that horrible smell is just gone.
It vanishes.
And instead, the whole lab starts smelling like fruit, maybe like pineapple or something.
It is quite the magic trick, isn't it? You
Yeah.
take two things that smell, well, pretty pungent, you cook them up, and boom, you get this really pleasant, fruity essence.
Exactly. It feels like alchemy. But, I mean, obviously, we aren't doing magic here. We're trying to study for the boards. So what is actually going on in that test tube?
That fruity smell is the result of a very specific and very important chemical reaction called esterification.
Esterification. Okay.
And that is exactly where we're heading today. We're doing a deep dive into the chemical reactions of carboxylic acids from
Mhm.
Unit 8, aldehydes, ketones, and carboxylic acids.
Unit 8, the big one. I think every student listening just felt a little bit of stress. That unit has a huge weightage,
It does. And most people just try to, ratify the equation.
which is the worst way to handle organic chemistry.
The absolute worst.
So beyond just the exam, why should we actually care? Why does a student need to know how vinegar turns into a banana smell?
Well, think of it like this. Understanding these reactions is like, it's the key to controlling matter. It explains how we make medicines, plastics, even how our own bodies work.
Okay.
And specifically, it explains why carboxylic acids are acidic when so many other organic compounds aren't. If you master this, you're not just memorizing the insert, you're learning how to actually build molecules.
I like the sound of that. Building molecules sounds much better than memorizing mechanisms.
It is.
So, okay, let's unpack this. We have our notes here. If you had to explain the core idea at the absolute simplest level, a zero-level explanation, what would you say? Simple. You just have to look at the structure. A carboxylic acid, RCOGUH, it's not one single block. You have to see that functional group as having two specific reactive sites.
Two sites. You mean like two different targets on the same molecule?
Precisely. It's like the molecule has a split personality.
Okay.
Imagine the molecule as a building. Site 1 is the acidic H. That's the hydrogen attached to oxygen. It's
Right.
Loosely held, so it's easily lost. That's why it acts as an acid.
Okay, so that's the acid part of carboxylic acid. That seems straightforward enough. What's the second site?
Site 2 is the electrophilic carbon. That's the carbon that's double bonded to the oxygen, the C=O group.
Right.
Now, this carbon is, well, it's hungry for electrons. It attracts things called nucleophiles. So conceptually, you're either attacking the hydrogen site 1 or you're attacking the carbon site 2.
That's a really helpful way to see it. I think a lot of us just see COOH as one big clump.
And that's the mistake.
So let's make this even clearer. I want everyone listening to just, close your eyes for a second. Unless you're driving or walking on the road, of course.
Yes, safety first. But if you're at your desk, just picture the carboxylic acid molecule. It's floating there, and it has these two distinct targets on it.
Got the image.
I see it.
Now imagine a base coming in, like NaOH. Bases are simple. They want protons. So they go straight for site 1.
The hydrogen.
The hydrogen on the oxygen, they just snatch it. That's it. But now imagine a nucleophile, like an alcohol molecule. Doesn't really care about the proton. It goes straight for site 2.
The carbon.
The carbon. So it's like different visitors knocking on different doors of the same house.
I like that. And this leads to what's really happening at the particle level, right? There's that big term.
Yes. The term you will see in your textbooks and marking schemes. Nucleophilic acyl substitution.
Whoa, hold on. Nucleophilic acyl substitution. That's a mouthful. Let's break that down because that sounds like one of those things students just write without understanding.
It sounds complex, but it's not. Here's what's happening. When a nucleophile attacks that carbon, the double bond breaks for a split second.
Okay, to make room.
To make room. But, and this is the crucial part, eventually a group has to leave. In carboxylic acids, that group is the OH.
The OH leaves. Wait, let me stop you there.
Go ahead.
This is where I think a lot of students get confused. We just studied aldehydes and ketones, right? They also have that CO group. Don't they just react the same way?
I'm so glad you asked that. This is the classic misunderstanding trigger. The #1 trap in the board exams.
Right.
Students think, oh, CO group must be an addition reaction like an aldehyde.
Exactly, because usually things just add on to the double bond, it breaks, things stick, and everyone stays in the molecule.
But here's the fix. Aldehydes and ketones do addition. Nothing leaves.
Oh.
But carboxylic acids do substitution. The OH group actually packs its bags and leaves.
That is a vital distinction. So aldehydes are addition, carboxylic acids are substitution. But why? Why does the OH leave? I thought OH was a bad leaving group.
That is a brilliant question. And you're right, in an alcohol, OH is a terrible leaving group. But here, that carbonyl oxygen, the CO, changes everything. When the nucleophile attacks, the double bond opens up. But oxygen loves being in a double bond. It wants to reform it. And when it swings back down to make that COU again, it kicks out the weakest link.
Which is the OH group.
In this case, yes. So the double bond reforming provides the kick to push the OH out.
Okay, I want to anchor this for everyone. For the exam, what's the official definition they should write?
The anchor definition is, carboxylic acids undergo reactions including proton donation, acidity, esterification, and nucleophilic acyl substitution due to the presence of both the acidic OH and the electrophilic CO.
Got it. Okay, to make this really stick, let's use an analogy. I saw one in the notes about a two-door office.
Yes, that's a great mental model. Think of the carboxylic acid as a busy office with two doors.
Okay, an office. I'm picturing it.
The acidic OH is the front door. This is where the simple visitors, the bases, come. They just interact with the doorman, the proton, and take them.
They take the doorman away. Got it. So they don't even really enter the office.
Barely. But then there's the other door. The carbonyl carbon is the back room, the main office.
Okay.
This is where the nucleophiles enter. But the back room is tiny. It's crowded. So when the new person, the nucleophile, forces its way in,
Someone has to leave.
someone inside has to leave via the exit. And that person leaving is the OH group.
I love that. So an aldehyde, what's its office like?
Aldehydes don't have an exit door. The groups attached are a carbon or a hydrogen, and they refuse to leave. So visitors just pile up inside. That's addition.
So aldehydes are a crowded room where nobody leaves. Carboxylic acids swap people out, one in, one out.
Exactly. One in, one out is the mantra for carboxylic acids.
That clears it up so much. But tell me, why does this whole concept even exist, historically or practically? Why is this swapping so important?
Well, without this concept, we literally couldn't synthesize most of the things we use every day.
Really?
Yes. This is the backbone of pharmaceutical synthesis-making drugs. It's how our body makes fats. It all relies on this swap.
And it's not new science, is it?
Not at all. Esterification, that fruity smell reaction, has been known since the 18th century. Chemists have been using this backroom trick for hundreds of years to create new materials.
Amazing. Okay, I want to run a mental movie for everyone. Let's really visualize this so you can see it in the exam hall.
Let's do it. Visualizing is always better than memorizing.
Okay. Imagine a carboxylic acid molecule, maybe acetic acid, sitting in the center of a white room. Now, 3 different reagents walk in.
Okay, character number 1. Region 1 is a base, let's say NaOH. It walks in, it sees the OH group, it just snaps up that proton.
Snatch! The proton is gone. What's the result?
You get a salt, a temoxylate ion.
And just to be clear, why is that ion stable? Why is the acid okay with losing its proton?
Crucial point. When that proton leaves, the negative charge left behind isn't stuck on one oxygen. It dances back and forth between the 2 oxygen atoms.
Resonance.
That is resonance stabilization. Because the charge is shared, the ion is relaxed. That's the real reason it's an acid.
Okay, so the base leaves us with a stable ion. Now, character 2 enters. Reagent 2 is an alcohol.
Right. The alcohol approaches, it ignores the proton, it goes for the carbon, the back room, it attacks.
Yeah.
There's a bit of a tussle, and then the original OH of the acid is kicked out as water.
And the result is?
An ester. Your fruity smell. The alcohol has replaced the OH. One in, one out.
Okay, last one, character 3. Reagent 3 is a reducing agent, like Lyl H4. This guy looks strong.
Oh, he is. This is a bulldozer. A hydride attacks the carbon deeply. It doesn't just swap once, it pushes the reaction all the way, kicks oxygen out, and you end up with a primary alcohol.
It strips the acid down completely.
You got it. That's the entire behavior profile of this molecule.
It's surprisingly logical when you break it down like that.
It is.
Let's go back to our first example, the fruity smell. Acetic acid plus ethanol gives ethyl acetate.
Correct. But here's a detail for the exam. That reaction is reversible.
Reversible, so the fruit smell can turn back into vinegar.
Yes, if you aren't careful. That's why you need an acid catalyst, like sulfuric acid. It does 2 things. First, it makes the carbon even more hungry for the alcohol. Second, it removes the water that's formed.
Le Chatelier's principle.
Exactly. If you remove a product, you force the reaction to go forward. That's a very common reasoning question to the boards. Why is water removed during esterification?
To shift equilibrium to the right. Got it. Now, what about something more serious? You mentioned medicines. Is there a famous drug that uses this chemistry?
Oh, absolutely. The most famous one, aspirin.
Wait, aspirin, as in the headache medicine?
Yes, aspirin is acetylsalicylic acid.
Okay.
You make it by taking salicylic acid and performing this exact acyl substitution reaction. You react its OH group to make an ester.
That is wild. The same chemistry that makes a fruity smell is what cures your headache.
The rules don't change just because the application changes.
Okay, now for a counterintuitive point. You might think, why doesn't the reaction just stop after the nucleophile adds on? Why does the OH have to leave?
That's the intuition from aldehydes, where you expect simple addition. But actually, nature hates instability. If you just added to a carboxylic acid, you would get an intermediate that is incredibly unstable.
Too much tension in the molecule.
Way too much. The only stable path forward is for the OH to leave. So nature chooses substitution because it leads to a stable product.
Nature finds the most stable path. Okay, we're nearing the end. This is the part where everyone listening should grab a pen. We're going to do the exam-safe clarity lines.
These are the golden rules, the lines that the examiners look for.
Okay, I'll say the topic. You give me the golden rule. Ready?
Ready.
Acidity.
Carboxylic acids are weak acids. They donate H+ to bases. The key point. This is driven by the resonance stabilization of the carboxylate ion. Don't forget the word resonance.
Esterification.
Reaction with alcohol plus an acid catalyst gives ester plus water. And remember, the reaction is reversible.
Mechanism type.
It is nucleophilic acyl substitution, not simple addition. Key point. If you write addition, you get 0 marks.
Leaving group.
The OH group leaves. It is substituted to allow the nucleophile to take its place.
Reduction.
Strong reducing agents like LyLH4 turn carboxylic acids into primary alcohols. It goes all the way.
And one last one. Decarboxylation.
Ah, yes. Removing the whole COH group as CO2 using soda lime and heating. This is how you make the carbon chain shorter by 1 carbon.
It's like you chop the head off the molecule.
Brutal, but easy to remember. It works.
Okay, let's wrap this up. A short summary for revision. This is what you need to retain.
Right. Let's boil it down. Number 1, carboxylic acids have 2 reactive sites, the acidic H and the electrophilic carbon.
2 personalities.
Number 2, think of the 2-door office, bases at the front door, nucleophiles at the back with a swap.
1 in, 1 out.
Number 3, the classic example is the fruity smell of esters from the lab. And finally, and most importantly, always remember substitution, not addition.
Because the OH is a good leaving group in this context.
Exactly. It's pushed out to maintain stability.
Perfect. So next time you see a reaction question on your exam paper, don't just see letters and lines.
No. Visualize that team swap, 1 player in, 1 player out.
That's the secret. Okay, final thought for you to think about. We talked about how acids turn into esters or alcohols, but what about the reverse? Can our body turn an alcohol back into an acid? Think about what happens when wine goes sour.
That is a story for another deep dive. But let's just say, oxidation is a powerful thing. It's the reverse movie of what we just watched.
Indeed it is. Thanks for diving in with us today. Good luck with Unit 8. Don't let the organic chemistry fear get to you.
Absolutely. Understand the logic, and the marks will follow. You've got this.
Catch you next time.